In the vastness of the cosmos, among the swirling galaxies and blazing stars, exists a substance so humble yet so consequential that it shapes the destiny of entire worlds. It drifts through the void, settles on planetary surfaces, and infiltrates the very air we breathe. This substance, cosmic dust, may appear insignificant to the casual observer, yet its influence extends from the formation of solar systems to the climate patterns of established planets, and perhaps even to the emergence of life itself. When we gaze up at the night sky, we witness light that has traveled across unimaginable distances. Yet what we cannot see with the naked eye are the countless particles of dust that populate the space between stars. These minute specks, typically measuring between 0.1 and 100 micrometers in diameter, are the silent architects of cosmic structure and planetary evolution. The story of cosmic dust begins in the fiery hearts of stars. As massive stars reach the end of their lives, they expel their outer layers into space, creating spectacular nebulae that serve as cosmic foundries. Within these stellar nurseries, elements forged in stellar cores, carbon, silicon, oxygen, iron, and more exotic materials, condense into microscopic grains. This process, first comprehensively described by astronomer Cecilia Payne-Gaposchkin in the 1920s, represents the birth of cosmic dust. In 1969, when Apollo 11 astronauts landed on the Moon, they encountered lunar dust firsthand. This fine, abrasive material clung to their spacesuits and equipment, causing unexpected problems. Astronaut Neil Armstrong reported that the dust had a distinctive odor, somewhat like spent gunpowder, when it was brought into the lunar module. This direct interaction with extraterrestrial dust provided scientists with valuable insights into the properties and behavior of dust particles in airless environments. The Moon's surface is covered with a layer of dust known as regolith, formed over billions of years by the continuous bombardment of micrometeorites. Without an atmosphere to slow them down, these tiny particles strike the lunar surface at high velocities, pulverizing rocks and creating a fine, powdery substance. This regolith holds a record of cosmic impacts and solar radiation, making it an invaluable resource for scientists studying the history of our solar system. Dust in our own solar system takes many forms. The zodiacal light, a faint, triangular glow sometimes visible after sunset or before dawn, is caused by sunlight reflecting off dust particles in the plane of the solar system. These particles, ranging in size from a few micrometers to several millimeters, originate from asteroid collisions and cometary outgassing. The study of this phenomenon dates back to the 17th century, when astronomer Giovanni Cassini first correctly identified its source. In 1983, the infrared astronomical satellite, IRAS, discovered dust disks around several nearby stars, including Vega and Fomalhaut. These observations, led by astronomer Fred Gillett, provided the first direct evidence for the existence of what would later be recognized as protoplanetary disks, the birthplaces of planets. This discovery revolutionized our understanding of planetary formation and established dust as a fundamental building block of solar systems. The process of planetary formation begins with these disks of gas and dust surrounding young stars. Within these swirling maelstrom, dust particles collide and stick together, gradually growing from microscopic grains to pebbles, then to boulders, and eventually to planetesimals, the precursors of planets. This process, known as accretion, was first mathematically modeled by Viktor Safronov in the 1960s and has since been refined through both theoretical work and observational evidence. In 2014, the European Space Agency's Rosetta mission made history by landing a probe on the surface of Comet 67P/Churyumov-Gerasimenko. The mission, led by project scientist Matt Taylor, collected data on the comet's dust composition, providing valuable insights into the primordial material from which our solar system formed. The dust particles analyzed contained complex organic molecules, suggesting that comets may have delivered the building blocks of life to early Earth. The interstellar medium, the space between stars, is also populated with dust. These particles, studied extensively by astronomer Donald Osterbrock in the 1990s, play a crucial role in star formation. When regions of the interstellar medium become dense enough, they begin to collapse under their own gravity, forming new stars. Dust particles within these collapsing clouds radiate away excess heat, allowing the contraction to continue until nuclear fusion ignites at the core. A new star is born. Interstellar dust also serves as a catalyst for complex chemistry in space. Hydrogen atoms adhere to the surfaces of dust grains, where they can combine to form molecular hydrogen. This process, elucidated by astronomer David Hollenbach in the 1970s, is essential for the formation of stars, as molecular hydrogen serves as a cooling agent during cloud collapse. Without dust to facilitate this reaction, the universe would look vastly different with fewer stars and planets. On Earth, dust takes many forms and serves many functions. Desert dust, composed primarily of mineral particles, can travel vast distances on atmospheric currents. In 1999, researchers led by Joseph M. Prospero at the University of Miami discovered that dust from the Sahara Desert regularly crosses the Atlantic Ocean, fertilizing the Amazon rainforest with essential nutrients like phosphorus. This transcontinental journey highlights the interconnectedness of Earth's ecosystems and the unexpected role dust plays in maintaining them. Volcanic eruptions inject massive amounts of dust and ash into the atmosphere, with profound effects on global climate. The 1815 eruption of Mount Tambora in Indonesia, studied extensively by climatologist Richard Stuthers, caused the year without a summer in 1816, when average global temperatures dropped by 0.4 to 0.7 degrees Celsius. Crops failed across the northern hemisphere, leading to the worst famine of the 19th century. This event demonstrated the powerful influence that atmospheric dust can exert on planetary conditions. Marine dust, particularly iron-rich particles, fertilizes the oceans and stimulates the growth of phytoplankton. These microscopic organisms, through photosynthesis, convert carbon dioxide into organic matter, effectively sequestering carbon from the atmosphere. Oceanographer John Martin proposed the iron hypothesis in 1990, suggesting that iron dust deposition in the oceans could regulate global climate by controlling the efficiency of this biological carbon pump. Subsequent research has confirmed the importance of dust-borne nutrients in marine ecosystems. At the microscopic scale, dust particles serve as condensation nuclei for cloud formation. Water vapor in the atmosphere condenses around these particles, forming droplets that eventually grow large enough to fall as precipitation. This process, described in detail by meteorologist Bernard Vonnegut, brother of novelist Kurt Vonnegut, in the 1940s, is fundamental to Earth's hydrological cycle. Without dust, cloud formation would be severely hindered, dramatically altering global precipitation patterns. The composition of atmospheric dust can also affect the radiative properties of clouds. In 2002, atmospheric scientist Daniel Rosenfeld demonstrated that pollution particles from industrial activities can inhibit rainfall by creating clouds with smaller droplets that do not readily coalesce and fall as precipitation. This finding highlighted the complex interplay between human activities, atmospheric dust, and global water cycles. Cosmic dust also plays a role in shielding planetary surfaces from harmful radiation. On Mars, dust storms can envelop the entire planet, altering its radiation environment. In 2001, the Mars Global Surveyor, under the scientific leadership of Arden Albee, observed a global dust storm that significantly reduced the amount of ultraviolet radiation reaching the Martian surface. This protective effect may have implications for the potential habitability of the red planet and the survival of any microbial life that might exist there. The study of Martian dust has been a focus of multiple missions to the red planet. In 2018, the NASA InSight lander, with principal investigator Bruce Bannert, deployed instruments on the Martian surface that were partially powered by solar panels. The accumulation of dust on these panels gradually reduced their efficiency, highlighting one of the practical challenges of operating equipment on Mars. Understanding the behavior of Martian dust is crucial for planning future missions, especially those involving human explorers. On Venus, dust takes on a different character. The planet's thick atmosphere contains sulfuric acid aerosols that reflect sunlight, creating the brightest object in our night sky after the moon. These particles, first detected by astronomers at the Lowell Observatory in the 1920s, contribute to Venus's extreme greenhouse effect, trapping heat and maintaining surface temperatures hot enough to melt lead. The study of Venusian atmospheric dust provides valuable insights into climate dynamics and the potential dangers of runaway greenhouse effects. Jupiter, the largest planet in our solar system, hosts dust rings that were only discovered in 1979 by the Voyager 1 spacecraft, under the guidance of project scientist Edward Stone. These faint rings, composed of small dust particles ejected from the Moon's Métis, Adrastea, and other bodies, represent a different manifestation of dust in planetary systems. Unlike Saturn's more famous rings, which contain larger ice and rock fragments, Jupiter's rings consist primarily of microscopic dust, highlighting the diversity of ring systems in our solar system. Saturn's magnificent rings, though composed primarily of ice fragments, also contain significant amounts of dust. The Cassini mission, led by project scientist Linda Spilker, studied these rings extensively from 2004 to 2017, revealing complex structures and dynamics. The mission discovered that meteoroid impacts on the rings generate clouds of dust that are influenced by Saturn's magnetic field, creating spoke-like features that rotate with the planet rather than following Keplerian orbits. This phenomenon, first observed by the Voyager missions in the 1980s, demonstrates the complex interaction between dust and planetary magnetic fields. Beyond our solar system, dust plays a crucial role in the formation of other planetary systems. The Atacama Large Millimeter/Submillimeter Array ALMA, which began operations in 2011 under the direction of Pierre Cox, has observed detailed structures in protoplanetary disks around young stars. These observations have revealed dust gaps, rings, and spirals that are likely caused by forming planets, providing a glimpse into the processes that shaped our own solar system billions of years ago. The James Webb Space Telescope, launched in December 2021 with John Mather as senior project scientist, represents the next frontier in the study of cosmic dust. Its advanced infrared capabilities allow it to peer through dust clouds that obscure visible light, revealing the processes of star and planet formation in unprecedented detail. The telescope's observations of dust in distant galaxies also provide insights into the cosmic history of element production and the conditions that eventually led to the formation of planets like Earth. Dust also plays a significant role in the search for extraterrestrial life. Astrobiologist Natalie Batalha, who served as the mission scientist for NASA's Kepler spacecraft, has studied how dust affects our ability to detect potentially habitable exoplanets. Dust disks around other stars can mimic some of the signals astronomers look for when searching for planets, complicating the interpretation of observational data. Understanding these effects is crucial for identifying true candidates for habitability in our galactic neighborhood. On Earth, dust has played a role in major evolutionary transitions. The asteroid impact that led to the extinction of non-avian dinosaurs 66 million years ago, studied extensively by geologist Walter Alvarez, ejected massive amounts of dust into the atmosphere. This dust blocked sunlight, causing a global cooling event that disrupted ecosystems worldwide. The resulting environmental changes created opportunities for mammals to diversify and eventually dominate terrestrial ecosystems, setting the stage for the emergence of humans millions of years later. Volcanic dust has similarly influenced human history. The massive eruption of Mount Toba in Indonesia approximately 74,000 years ago, studied by anthropologist Stanley Ambrose, coincided with a genetic bottleneck in human populations. This suggests that the volcanic winter caused by dust and aerosols ejected into the atmosphere may have brought human populations to the brink of extinction. Our species' survival through this crisis represents one of the most significant close calls in our evolutionary history. More recently, the Dust Bowl of the 1930s in the American Great Plains demonstrated the devastating consequences of poor land management practices. Soil scientist Hugh Hammond Bennett documented how the removal of native vegetation, combined with prolonged drought, allowed winds to strip away topsoil, creating massive dust storms that darkened skies across the continent. This environmental disaster led to the establishment of the Soil Conservation Service, now the Natural Resources Conservation Service, in the United States, and fundamentally changed agricultural practices across the world. The study of dust in ice cores has provided valuable insights into Earth's climate history. In the 1990s, glaciologist Lonnie Thompson extracted ice cores from mountain glaciers around the world, revealing dust deposits that corresponded to major climatic shifts over hundreds of thousands of years. These records show that during glacial periods, atmospheric dust levels increased dramatically due to expanded deserts and stronger winds. This research has been instrumental in understanding the complex feedback mechanisms that drive global climate cycles. Household dust, though seemingly mundane, has become an important subject of scientific inquiry. Microbiologist Noah Fearer at the University of Colorado Boulder has studied the microbial communities that inhabit indoor dust, finding that they reflect both the outdoor environment and the human occupants of a space. His research, published in 2015, revealed that the dust in a home contains a microbial fingerprint of its inhabitants, including both humans and pets. This work has implications for understanding the relationship between indoor environments and human health. The health impacts of dust extend far beyond household allergens. In 2005, epidemiologist Anthony J. McMichael compiled evidence linking desert dust to the transport of pathogens across continents. His research showed that African dust carries bacteria and fungi to the Caribbean, potentially contributing to coral reef diseases. This work highlighted the unexpected ways in which dust can influence ecosystems and human health on a global scale. Industrial activities have introduced new types of dust into the environment, with sometimes severe consequences. The black lung disease that affects coal miners, studied extensively by physician William Davis in the 1960s, is caused by the inhalation of coal dust. Similarly, silicosis, resulting from exposure to silica dust in mining and construction, has been recognized as an occupational hazard since the early 20th century. These diseases underscore the importance of understanding and regulating dust exposure in industrial settings. Nanodust, particles smaller than 100 nanometers, represents a frontier in dust research. Materials scientist Vicky Colvin has investigated how engineered nanoparticles interact with biological systems, finding that their small size allows them to penetrate cellular barriers that exclude larger particles. This research, which gained prominence in the early 2000s, has implications for both the potential health risks of nanomaterials and their applications in medicine and technology. The electrical properties of dust can lead to unexpected phenomena. On Mars, dust devils, swirling vortices that lift dust into the atmosphere, generate static electricity through the friction of particles. This process, studied by planetary scientist William Farrell at NASA's Goddard Space Flight Center, creates electric fields strong enough to affect chemical reactions on the Martian surface. These electrically charged environments might facilitate the formation of complex molecules, with potential implications for the chemistry of life. In 1977, astronomer James Oberg documented cases where cosmic dust entering Earth's atmosphere was mistaken for UFOs. These fast-moving particles can create bright streaks of light that appear to change direction as they encounter different layers of the atmosphere. This work highlighted how dust can create optical illusions and contribute to misinterpretations of atmospheric phenomena. The protective qualities of dust extend to the preservation of archaeological artifacts. In 2006, archaeologist Sarah Parcak used satellite imagery to identify ancient Egyptian settlements buried beneath layers of desert dust. These sites, preserved for thousands of years by their protective covering, provide valuable insights into ancient civilizations. This application of remote sensing technology to archaeology demonstrates how dust can serve as a time capsule, preserving the past for future generations to discover. In the field of materials science, dust has inspired innovative technologies. Engineer Joseph Wong at the University of California, San Diego, developed microrockets in 2012, tiny particles that propel themselves through fluids by generating bubbles. These self-propelled particles, inspired by the movement of dust in liquids, have potential applications in targeted drug delivery and environmental remediation. This work exemplifies how studying the behavior of dust can lead to technological breakthroughs. The interaction between dust and light has practical applications in astronomy. In 1989, astronomer Andrea Ghez used the technique of speckle interferometry to overcome the blurring effects of atmospheric dust and turbulence, allowing for clearer observations of celestial objects. This technique, which involves taking many short exposures and combining them computationally, has been instrumental in studying the center of our galaxy and providing evidence for the existence of a supermassive black hole there. On a more philosophical level, the study of dust connects to fundamental questions about our place in the universe. As astronomer Carl Sagan famously noted in his 1980 television series, Cosmos, "We are star stuff. The elements that compose our bodies were forged in stellar furnaces and distributed through space as dust." This poetic truth, grounded in solid astrophysics, highlights the deep connection between cosmic processes and human existence. The future of dust research lies in understanding its role in planetary habitability. In 2010, astrobiologist David Catling proposed that the presence or absence of dust could be a significant factor in determining whether a planet develops and maintains conditions suitable for life. His work suggests that dust's effects on climate, including its role in cloud formation and radiation balance, may be as important as factors like distance from a star in defining habitable zones around other stars. Recent research by atmospheric scientist Jasper Koch at UCLA has revealed that the cooling effect of atmospheric dust has masked some of the warming caused by greenhouse gases. His 2017 study indicated that as air pollution regulations reduce dust emissions from human activities, this cooling mask may diminish, potentially accelerating climate change. This finding underscores the complex and sometimes counterintuitive ways in which dust influences planetary systems. The presence of dust in the early solar system also influenced the distribution of water and other volatile compounds. In 2019, planetary scientist Rebecca Martin demonstrated that the snow line, the distance from the sun beyond which water could exist as ice, was affected by the presence of dust in the protoplanetary disk. This work helps explain why Earth and other inner planets are relatively dry compared to bodies in the outer solar system, with implications for the search for habitable worlds elsewhere. The electrical properties of dust may have played a role in the origin of life on Earth. In 2007, physicist Terence Key proposed that mineral dust particles could have served as templates for the assembly of the first biological molecules. The surfaces of these particles, with their complex electrical charge distributions, could have attracted and organized organic compounds, potentially catalyzing the formation of more complex structures. This hypothesis connects the seemingly mundane phenomenon of dust with one of the greatest mysteries in science: how life began. On Mars, dust storms have shaped the planet's geology over billions of years. The Mars Reconnaissance Orbiter, led by scientist Richard Zurek, has observed how these storms transport material across the planet's surface, eroding some features while burying others. This process has created the distinctive layered deposits found in many Martian craters, providing a record of the planet's climatic history. Understanding this record is essential for reconstructing Mars's transition from a warmer, wetter world to the cold desert we see today. The study of lunar dust has taken on new importance as space agencies plan to return humans to the moon. Geologist Sarah Noble at NASA has investigated the properties of lunar dust with an eye toward mitigating its harmful effects on equipment and human health. Her research, conducted in the 2010s, has shown that the sharp, glassy nature of lunar dust particles makes them particularly dangerous if inhaled. This work is informing the design of habitats and spacesuits for future lunar missions. Even in the outer solar system, dust plays a crucial role. The Cassini mission discovered geysers of water ice and dust erupting from Saturn's moon Enceladus, as reported by planetary scientist Carolyn Porco in 2006. These plumes, which feed Saturn's E-ring, suggest the presence of a subsurface ocean that could potentially harbor life. The analysis of dust particles within these plumes has revealed the presence of complex organic compounds, strengthening the case for Enceladus as a target in the search for extraterrestrial life. Dust rings have been detected around Uranus and Neptune as well, first by Voyager 2 under the scientific leadership of Edward Stone, and later studied in more detail by ground-based telescopes. These rings, much fainter than Saturn's, consist primarily of dark dust particles, possibly originating from impacts on the planet's moons. Their study provides insights into the collisional history and dynamics of the outer solar system, complementing what we know about the inner planets. The most distant dust in our solar system forms the Kuiper Belt and the Oort cloud, reservoirs of icy bodies that occasionally venture into the inner solar system as comets. Astronomer Jan Oort first proposed the existence of this distant cloud in 1950, though it has never been directly observed. These regions represent the boundary between our solar system and interstellar space, and the dust and small bodies they contain preserve information about the early formation of our planetary system. Interplanetary dust particles, IDPs, collected in Earth's stratosphere have been studied extensively by NASA scientist Donald Brownlee since the 1970s. These tiny particles, captured by aircraft flying at high altitudes, represent samples of the solar system delivered directly to Earth. Analysis of their composition and structure has revealed a diversity of materials, including pristine samples from the early solar system that have not been significantly altered since their formation 4.6 billion years ago. On Venus, dust may play a role in the planet's mysterious atmospheric dynamics. In 2020, Jane Greaves and her team at Cardiff University detected phosphine in Venus's atmosphere, a gas that on Earth is primarily produced by biological processes. While the finding remains controversial, one proposed explanation involves dust particles in the Venusian clouds hosting microbial life that produces phosphine as a metabolic byproduct. This hypothesis, while speculative, highlights how dust can create microenvironments with conditions very different from their surroundings. Jupiter's moon Io, the most volcanically active body in the solar system, ejects dust and gases that form a torus around the planet. This feature, first observed by the Voyager missions and studied in detail by astronomer Nicholas Schneider in the 1990s, demonstrates how a relatively small body can influence an entire planetary system through dust production. The interaction between this dust and Jupiter's magnetic field creates complex plasma phenomena that affect the entire Jovian system. On Earth, dust has historically been viewed as a nuisance, but its ecological importance is becoming increasingly recognized. Ecologist Emma Aronson at the University of California, Riverside, has studied how airborne microbes attached to dust particles colonize new environments, contributing to soil formation and ecosystem development. Her work, published in the 2010s, reveals dust as a vector for microbial dispersal that shapes biodiversity patterns across continents. The movement of dust across Earth's surface has been dramatically affected by human activities. In 2015, geographer Natalie Mahold at Cornell University quantified how changes in land use have altered global dust emissions, with some regions experiencing increases due to desertification and others seeing decreases due to vegetation changes. These alterations to natural dust cycles have cascading effects on ocean productivity, air quality, and climate patterns worldwide. The impact of dust on human respiratory health, has been studied extensively by epidemiologists Vera Vidal. His research in the 2000s demonstrated that exposure to particulate matter, including dust, is associated with increased rates of respiratory and cardiovascular disease. This work has informed air quality standards and public health policies around the world, highlighting the direct connection between environmental dust and human well-being. The behavior of dust in microgravity environments presents unique challenges and opportunities. Engineer David Carrier, who worked on the Apollo program in the 1960s and 1970s, studied how lunar dust would behave in the low gravity of the moon. His work predicted many of the problems astronauts would encounter, including the tendency of dust to cling to surfaces due to electrostatic forces. This research is now being revisited as space agencies prepare for a return to the lunar surface. In the search for extraterrestrial intelligence, dust presents both challenges and opportunities. Astronomer Jason Wright at Penn State University has proposed that advanced civilizations might build megastructures around their stars, which could be detected by the infrared emission from dust heated by starlight. His work, published in 2016, suggests that looking for anomalous dust signatures could be a viable strategy in the search for technological civilizations beyond Earth. The study of cosmic dust connects to fundamental questions in physics. Physicist Lawrence Krauss has investigated how dust grains in interstellar space absorb and remit photons, contributing to the thermodynamic arrow of time. His work in the 1990s suggested that the interaction between radiation and dust helps explain why we experience time as flowing in one direction, connecting microscopic dust interactions to one of the most profound mysteries in physics. In the field of computer science, dust has inspired algorithms for distributed computing. Computer scientist Radhika Nagpal developed the Kilobot system in 2012, consisting of simple robots that communicate and coordinate their actions like particles in a dust cloud. This approach to swarm robotics demonstrates how studying the collective behavior of dust can lead to innovations in artificial intelligence and distributed problem-solving. The most profound implication of cosmic dust may be its role in creating the conditions for consciousness to emerge in the universe. Neuroscientist and philosopher Patricia Churchland has explored how the evolution of nervous systems, made possible by the elements distributed through space as dust, eventually led to the development of self-awareness and subjective experience. This perspective places dust at the beginning of a causal chain that leads to the emergence of minds capable of contemplating their own origins. As we look to the future, dust will continue to shape the evolution of planets, including our own. Climate scientist Veena Patel has modeled how changes in dust production and transport due to climate change will affect marine ecosystems, with potential impacts on carbon sequestration and global food webs. Her work, published in 2021, highlights the need to incorporate dust dynamics into climate models to accurately predict future environmental conditions. The engineering challenges presented by dust on other worlds will need to be overcome for human exploration to succeed. Materials scientist Nathan Vorontsov has developed dust-resistant coatings for solar panels and optical instruments, inspired by the lotus leaf's ability to repel particles. His innovations, patented in 2019, represent a practical application of biomimicry to solve problems posed by extraterrestrial dust. In the coming decades, dust from human activities in space, including mining asteroids and constructing habitats, may become a significant factor in near-Earth space. Orbital debris specialist Kalpana Kanakarajan has modeled how this anthropogenic space dust might interact with satellites and space stations, identifying potential hazards and mitigation strategies. Her work anticipates the challenges of managing the human footprint beyond Earth as our species extends its reach into the solar system. Perhaps the most profound lesson from the study of cosmic dust is one of perspective. In the words of astrophysicist Neil deGrasse Tyson, we are all connected to each other biologically, to the Earth chemically, to the rest of the universe atomically. The dust that shapes planets, enables the formation of complex chemistry, and ultimately contributes to the emergence of life, reminds us of our intimate connection to cosmic processes. From the hearts of dying stars to the cells of our bodies, dust traces a continuity that spans billions of years and light-years of space. As we continue to explore our solar system and beyond, the study of dust will remain central to understanding the past, present, and future of planets, including our own. In the words of astronomer Carl Sagan, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." The humble dust particle, so small as to be invisible to the naked eye, carries within it the story of our origins and perhaps the key to our destiny among the stars.